Here we go. Let's get started. Welcome everyone to 7.2b. 7.2b is going to be a little longer than 7.2. That's a 4. 7.4b is going to be a little longer than 7.4a, but I'm going to be try to keep things a little brisk today. So the last thing we were doing is we were looking at all 6 trig function values of all angles using reference angles and stuff like that. So let's do a couple more of these. Example 3 is what we're on. We'll do a couple more practice. This should be very familiar to you by now. Okay, so we're only going to do a few of these. So find exactly the following. So part A is going to be secant of pi over 6. So again, I say this is almost nothing new because essentially all this is just find what cosine of pi over 6 is and then reciprocate it. So again, you will always have these special triangles. 30, 60, 90 triangle is 1, 2, root 3, and 45, 45, 90 triangle. Sometimes I use degrees, sometimes I use radians, trying to get you guys comfortable with both. All right. So pi over 6, right? That's 30 degrees. Secant's like cosine. Cosine would be root 3 over 2. Secant's the reciprocal of that, so it's just 2 divided by root 3. All right. So that's essentially all it is. And then, of course, there are harder versions of this problem, right? Like, let's go to part B, which is really kind of obnoxious. We look at cotangent of 13 pi over 6. This is pretty obnoxious because we have to deal with cotangent. We've got a big angle. Who knows what that angle is? But we just draw a picture, okay? We need to find out, first off, where 13 pi over 6 is. Turning this into degrees really might help you. It might help you a lot. But let's go off to the side and say, okay, 13 pi over 6. Well, that's 12 pi over 6 plus pi over 6. Well, what is 12 pi over 6? If you reduce that, that's just 2 pi. So here we are. We just go all the way around the circle and then go pi over 6 more. So joke's on you, same triangle as over here. And again, this is just a 30, 60, 90 triangle again. Tangent is opposite over adjacent. Cotangent is adjacent divided by opposite. It's just the square root of 3 right here. Okay? So not much to this. We'll do one more just to really beat this into the ground. Secant of 3 pi over 4. So this is what I said last section when I said 7.4 should be pretty good for most of you guys because half of it is just stuff we've already done. We did all of this in 7.3. 3 pi over 4 is 135 degrees, has a reference angle of 45 degrees, or pi over 4. We use our triangle, it's 1, 1, root 2. Where do the negatives go in the second quadrant? Your x-coordinate's negative, so you put a negative right there. Secant is the reciprocal of cosine. Cosine would be adjacent over hypotenuse. Secant is the reciprocal, that's hypotenuse over adjacent. Root 2 over negative 1. We can just simplify that as a negative square root of 2. All right, and that's really the first half of the section. This is kind of like a halfway point for us. So then, let's start doing some new stuff. We're going to be integrating some stuff that you've learned before in other classes with trigonometric functions. All right, so here we go. Let's first start talking about even and odd functions. Okay, so recall even and odd functions. Now, one of the ways that I remember what the heck is an even function and what the heck is an odd function is thinking about polynomials. And the thing about polynomials is if you have an odd monomial, then that's an odd function. If you have an even monomial, that's an even function. So what I mean by that, remember, is let's look at a parabola. Y equals x squared. Monomial just means only one term. Well, this is symmetric. Even and odd have to do with symmetry. So this is symmetric right here. It's reflected on the left and it's reflected on the right. An odd function, we could look at x cubed, and that's an odd function. And it's sort of reflected around both axes. And by sort of, I mean it is. So this is symmetric about the y-axis, and this is symmetric about if you reflect it both ways, then it's symmetric. Or if you rotate it at 180 degrees is another way of thinking about it. If we rotate this thing 180 degrees, we are still on the graph. So that's essentially what we're talking about here. So in chapter 8, we're going to start talking about graphs. And I know you're all excited to get there, and I know you want to wait and savor the moment as well. But I'm just going to show you some graphs of sines, cosines, and tangents. So let's look at some graphs. This is a graph of sine of x. Very similarly, this is the graph of cosine of x. So right off the bat, you should know something. You should notice something. There's some similarities between what we drew above. Cosine, notice, is symmetric about the x-axis. So cosine's got to be even, right? There's that same symmetry in cosine that there is for x squared. Similarly, the same sort of symmetry in x cubed can be found in sine of x. Sine of x is an odd function. All right? And I'm not going to show you the graphs of the reciprocal functions, but suffice it to say that if you have an odd or an even function, its reciprocal function is also odd or even. So anyway, the last thing I do want to talk about is tangent. Tangent is a funny one. Not as funny as the reciprocal ones. Don't worry, we'll talk about the reciprocal ones eventually. But tangent looks very similar to a cubic function, but it has asymptotes. And has infinitely many asymptotes. And it just kind of keeps asymptoting forever. So it just does this forever. But again, we have that same sort of, it looks like a cubic. It's not, but it looks kind of like that. This is even as well, or odd as well. Okay. So a lot of people may forget about what the definition of even odd means. We just think of symmetry, but mathematically what symmetry means is that if it's odd, that means that f of x equals negative f of negative x. And if it's even, that f of negative x equals f of positive x. This is one definition for even and odd. That if we put in a negative x, we get a negative f. Here, if we put in a negative x, we get the positive f. In fact, a lot of times you'll actually see this negative over here, right here. They're equivalent definitions though. So anyway, we're going to talk about how this works for trig functions. So sine of theta is odd. So it's negative sine of negative theta. We're just using the definition of an odd function and writing it for sine. We're going to list them all, but really, once you know whether a function is even or odd, it's kind of the same thing. Cosine of theta is cosine of negative theta. Again, we're just using the definition of even and odd. But here the function, f of x, is cosine of theta. Okay, tangent is odd, so we use a definition for an odd function, just like sine. And the reciprocal functions are all exactly the same. Okay? So cosecant theta equals negative cosecant of negative theta. Secant theta is also even. It's secant of negative theta. And cotangent of theta is also odd. Yeah, cotangent of theta is also odd. So it's negative cotangent of negative theta. I was trying to remember what cotangent looked like in my head. And actually, cotangent looks very similar to tangent. Yeah, so there we go. So these are some more identities using the fact whether they're even and odd. Good news, again, remember, I'm not going to make you memorize identities, even though I think you can remember these probably, but I'm not going to make you. I will give identities, the identities that you need, I will give to you on quizzes and stuff. Okay. So anyway, let's use this. So we have some baby examples. They're nice baby examples. They should be nice and chill and smooth and easy. I don't think babies are easy and chill, but whatever. They're small examples. Small adult examples, maybe. All right. If secant of theta equals 2, the question is, what is secant of negative theta? So we know it's one of two things. If secant's odd, then it's going to be the opposite, negative 2. If secant's even, that means it's going to be the same, which is 2. Because remember, if it's even, that means a negative on the inside doesn't matter. If it's odd, a negative on the inside means there's going to be a negative on the outside. Secant is a reciprocal function of cosine. Cosine was even. Again, we'll talk a lot more about what graphs look like in chapter 8, which we're going right after chapter 7. But this is what cosine look like. So cosine is even. So secant is even. So this is also going to equal positive 2. All right. So we can just do a couple more of these, right? If cotangent of theta equals root 3, what is cotangent of negative theta? So again, we have to think of cotangent. All right, cotangent is the same as tangent. And again, you're not going to be super familiar with the graphs, and you'll have these identities with you anyway, but we're sort of getting to graphing a little early. We're just kind of sliding it in, getting you a little exposed to it. All right, this is odd. This kind of looks like x cubed. X cubed is odd. 3 is odd. Great, so it's an odd function. So if it were even, it'd just be the same. But if it's odd, it's the opposite. So we get negative root 3. And that's all there is to it. Just using the fact that whether something's even or odd. Okay? Let's have it again. This section is kind of wrapping things together in chapter 7 and teasing the future. We teased chapter 8. Next, we're going to tease chapter 9. There's a property that we've talked about this a bit, but it essentially says that tangent of an angle is sine of that angle divided by the cosine of that angle. And again, if you just simplify this, this is opposite over hypotenuse. This is adjacent over hypotenuse. The hypotenuse is canceled and you get opposite over adjacent, which is tangent. So you can see where this comes from. And likewise, right, cotangent is the reciprocal, so that's going to be cosine theta over sine theta. One of the cool things we're going to do in chapter 9 is start talking about trigonometric identities and trigonometric equations. Here are some baby ones here, really well behaved, really nicely behaved ones. We've already introduced a bunch of trig identities so far, but we're really going to hit it with a hammer in chapter 9. It should be a good time. So example 6. Given, well, all right, trig identities would be example 7. Given that sine of theta equals root 2 over 2 and cosine of theta equals root 2 over 2, find tangent of theta. And there's 2 ways of doing this. There's an easy way and there's a hard way. And honestly, I'm not sure which way is which. Okay? But one of the ways, we could draw a triangle, right? These are both positive, it has to be in the first quadrant. And for tangent, it's going to be sine over cosine. So we could draw the angle and find what tangent is that way, but let's use this new handy dandy trig identity that we have right here. So tangent of theta is sine over cosine. Yeah, I already got the right answer in chat. Very good. So it's going to be root 2 over 2 divided by root 2 over 2. Now, there's a couple of ways. Hold on. There's a couple of ways to simplify this. We could write it as division. We could multiply by the least common denominator on the top and the bottom. But really, we don't have to, because this is the same thing on the top as it is on the bottom. The whole fraction cancels, and it just goes to 1. Excellent. Okay? So, that's essentially this. Let's do some trig identities. Example 7. So we have simplify. Part A, secant t over tangent of t. And part B is going to be tangent of theta, cosine of theta. Okay? So, what we're going to do here is just rewrite tangent in terms of sines and cosines. And in fact, we're going to put everything in terms of sines and cosines. When we get to chapter 9, everything is going to be sines and cosines when we're trying to simplify trig identities and trig properties and stuff like that. Okay? So, first off, let's write this as secant of t divided by tangent of t, because I really don't like complex fractions. So let's get rid of the complex fractions. Okay? So what is secant of t? We want everything in sines and cosines. That is another way of rephrasing this. Put everything in sines and cosines and get some cancellation. Okay? Secant's 1 over cosine. Divided by tangent, which is sine over cosine. And now we have to use the division. So, you know, dividing fractions. You may have heard of like the phrase keep it, change it, flip it. That means keep the first fraction together, change the division and multiplication, and flip the second fraction. And here we are, beautiful, beautiful. Cosines cancel, and we get 1 over sine of t. This is an okay final answer. If you also want to write cosecant of t, I'll accept that. So you can use either one. They're both a-okay. Right? And that's essentially how you do it. You just put things in sines and cosines. Part B is even easier. Cosine is already in terms of sine and cosine, and tangent's just sine over cosine. So tangent's sine theta over cosine theta. Also, quick disclaimer, a lot of times we shorthand math as well as we shorthand speaking. So we'll say sine over cosine. That doesn't really make any sense. What we really mean is sine of an angle divided by cosine of an angle. These are functions. Functions have no meanings without inputs. So it's sine of theta divided by cosine of theta. Okay? And then again, it's getting multiplied by cosine. Multiplying a fraction by something that's not a fraction, well, let's make it a fraction. Divided by 1, cosines cancel, and we get sine of theta. So that's super easy. Trig, simplifying trig expressions, super easy so far. It'll get harder in chapter 9, but you have been introduced to it. We're just kind of starting you off with baby steps. All right, and really there's only a couple more examples left. Sections flying by. Let's do example 8. And I know, I'm going to tell you right now, when you see this example, you're going to stamp your foot and slam your hand into the wall and say, Jason, we've already done this. Perfect. Chapter 7.4, the section we're doing right now, is sort of a summary of chapter 7 and kind of weaning you into chapters 8 and 9. So you should have seen this before. If cosine of t equals 12/13 and t is in quadrant 4, find the other 5 trig function values. So yeah, we've already done this. Okay. So let's do it again. A couple ways of doing this. We could use our handy dandy formula. We could draw a picture. There's a lot of things that we can do. Let's just do this the way we've always been doing this. Why do something different if you don't have to? So t's in the 4th quadrant. I don't know what this triangle looks like, but it's going to be in the 4th quadrant. Okay? And the cosine is 12/13. So let's draw a triangle. Again, this is not the only triangle. We could have done 24 and 26. That has the same ratio of 12/13. But it doesn't matter. And you can use the Pythagorean theorem to say, okay, 12 squared plus, I don't know, whatever that is, let's call it y squared, equals 13 squared, and solve for y. You know, subtract the 144, take the square root. What you're going to get is 5, I think. Square root of 169 minus 144. That's going to be 25. Yeah, you're going to get 5. And again, it's going to be negative because the y part is going down. The y coordinate is down if you're looking at this point. So now we just start grinding it out. We already know cosine, but we need to know what sine is. Oh, we're not using thetas. We're using t's. That's a t somehow. Yep, now it's a t. So we already have cosine. So let's find sine, tangent. Let's find cosecant. Let's find secant. Now let's find cotangent. So we already found it. Sine, negative 5/13. Tangent, opposite over adjacent. Negative 5/12. Cosecant's the reciprocal. We already found it. Negative 13/5. We've already done this. Secant's the reciprocal of cosine. 13/12. Cotangent's the reciprocal of this. Negative 12/5. Easy. We've done this a million times now. All right. So let us do the last example problem of the section. Oh, I'm very sad. I have to break out a whole new piece of paper for just one problem. It's going to be so wasted. All right, what number are we on, though? I'm not good at counting. Example 9. This is kind of a neat little problem. Okay, so h equals 16 cosine of 1 divided by 500d. So we're going to deal with some functions now. We're going to use this function to solve an application. So this is something with, it's going to have a really long period, so it's going to oscillate very slowly. Got an amplitude about 16. All right. And anyway, what this is going to do is this represents the hours h of daylight. On the dth day of the year in some city. Again, this depends on how north or south you are. So in this city, it can be modeled like this. So the question is about how much sunlight is there on September 24th? And that's the 267th day, by the way. So you don't have to count that all up. So I'm going to actually interrupt this problem and get very confused. I'm almost positive I wrote this problem down correctly, but it makes no sense. Because if you know anything about trig functions, and you may not know this yet, this means the amplitude is 16. That means it goes 16 up and 16 down. So the longest day of the year is going to have 16 hours of sunlight, and the shortest day of the year is going to have negative 16 hours of sunlight. This problem must have been written down incorrectly, right? We're not going to have negative 16 hours of sunlight. Let's go on a tour. All right. So I stole this problem from the book. What? All right, we'll do the problem. I'll look into this afterwards because this makes no sense to me. If you know what this function looks like, this makes no sense to me. Well, whatever. Sorry about that. We'll talk about it later. Hopefully our answer makes sense. Goodness. Again, this book is, maybe I just don't understand something. Maybe I'm missing something. Let's do the problem. So on the September 24th, that is the 267th day. So we just take that 267, plug that right into D. Okay. So that's all it is. Just plug it in. We get 16 times the cosine of 267 over 500. And now don't go drawing triangles right now. Cosine of 267 over 500. You're not going to be able to figure that out on your own. You're going to have to use a calculator. But here is the very important question. Is this measure, is this inside, is this a degree or is this a radius? The answer is it's always a radian. I said radius. It's always a radian. Okay? Every application is always, not every, but almost every application ever is going to be using radians. And the reason for that really is related to calculus, so I'm not going to explain it here, but there's a good reason why essentially everything's going to be in radians. All right, so let's go plug this into our calculator and see what we get, making sure that our calculator is in radians. 16 times the cosine of 267 divided by 500. Please don't be a negative number. Okay, this is going to be 13.7724, or roughly 13 3/4, right? Roughly 13 hours and 45 minutes. Really roughly. We can maybe approximate it better, right? You could write this as 13 hours and 0.7724 minutes. And 7724 minutes is like 46 minutes. All right, it rounds to 46 minutes. So this answer at least makes sense in September, but we'll see what this means. I'm gonna have to think about this. I can get back to you if anyone has questions about what my findings are. I'll investigate it for my own curiosity. You can send me an email. I'll let you know what I find. Anyway, that's it. This whole section, that's the whole chapter. We're done for the week. Next week are going to be very light lectures. Going to be streaming a little bit of review. I've got a review sheet posted in Canvas right now. And if I don't have it posted in Canvas right now, I will post it very shortly. So it will be there when you see it. We're going to be doing some review problems next week, and the exam will open up next week as well, but you'll have a week to take it. So this week is just the quiz on 7.3 and 7.4, but next week will be the exam. Anyway, hope you have a great time. Good luck on the exam. Feel free to let me know if you have questions as you're studying. Bye.